LabTech Innovations.
My dear students, let me tell you a quotation from one of the greatest mathematicians of the world. Is called René Descartes, the one after whom this Cartesian geometry is named. You know what he says? He says that I am because I think, and thinking is essential to being a human being, right? So thinking is the basic core of mathematics. And the chapter that I'm going to take now will require a lot of thinking on your part, right? So it's like a exercise to your brain, exercising your intellect, So this is one of the most beautiful topic, and it doesn't require much of a mathematics from the other parts. I mean, it's a standalone kind of a topic. The topic that is required, the kind of background that it requires is permutation combination, that chapter which we have already done, permutation combination. And after that, you just need your common sense. Of course, you must come here with your common sense. Remember, common sense is highly uncommon, right? Okay, fine. So let us start with this chapter called probability. Probability has got a very infamous origin, because probability started with those people who were interested in gambling, So whenever you are gambling, there is an element of chance, and they always wanted to find out what are the chances of their winning. And they asked mathematicians to find out, is there any method of finding out whether they will win or lose, So like that, these kind of questions led mathematicians to create a science of chances, or predicting the chance, right? And that is called probability. So probability. So in probability, we deal with experiments. Now, these are not the scientific experiment that we generally do in our science laboratories, right? In science laboratories, we are not experimenting, actually speaking. We are only verifying the rules which are already in existing. For example, if you want to verify Newton's law, so you throw a chalk, and then when it comes down, then according to Newton's law, it has come down. So outcome is already decided, and you know it, and you are just verifying it. So that kind of verification is not an experiment at all. The kind of experiment that we are talking about are those experiments whose outcome cannot be determined, right? So they are called random experiments, right? So that experiment which has got more than one outcomes, So that is called experiment. So let us start with experiment, the concept of experiment itself. Experiment, a physical phenomena which has more than one outcome. Now, what kind of experiments are there which has got more than one outcome? There are many. For example, you just take a box of cards. So there is a box of cards, and there are some, there are certain cheats. Each cheat is containing one number, say from 1 to 10. So there are 10 numbers lying there, right? Written on every cheat, right? And you are selecting one cheat out of that. So the outcome is not more than one outcome here, because there are 10 outcomes possible here, right? It could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So that is called random experiment, which is why it has more than one outcome. Or let us take a simple example. When you toss a coin, if you toss a coin, then there is either head or there is tail. So there are two outcomes possible. So it fits into the definition of an experiment. Okay. Now, if you take a pack of cards, for example, you shuffle it and then just pick up one card out of it. So we do not know what kind of card it is. So there are many outcomes, 52 outcomes in fact possible. So therefore, this kind of experiments like throwing a coin, tossing a die, or choosing a card out of a pack of cards, these kind of experiments where the outcomes are more than one, they are called experiments. So one famous examples which we'll be using again and again, I'll write here. So let us take an example of an experiment. So first experiment is the simplest of the time, tossing a coin. Tossing a coin. When you toss a coin, there are two outcomes possible. One is head or another is tail. So there are two outcomes possible. So this is an experiment, right? Two outcomes possible. Now, for example, second experiment is what? Selecting a card or cards, selecting a card or cards, whatever, right? Out of a pack of 52 cards, playing cards. Okay, that is another experiment which will be doing quite often, right? One of the another favorite experiment that we always deal with is tossing a die, throwing a die. I understand you should know what is a die. Die is a cubical, cubical surface. Each says 1, 2, 3. So there are 6 faces. So that throwing a die has got 6 outcomes. It will be either, uppermost face. This is the outcome face. So it will be either 1, 2, 3, 4, 5, or 6. Right? So these are the typical experiments that we'll be dealing with, and plus there are many others. But these are the examples of experiments. So these are the experiments, and these are the examples of that. So these are the examples of experiment. Okay. So now I think it is very clear for you what is the meaning of experiment. Okay. And of course, remember, tossing a coin is not the only experiment. Instead of tossing a coin, we can toss 2 coins. If you toss 2 coins, the number of outcomes will be increased. Selecting cards, if instead of 1 card, suppose you select 2 cards, then again the outcomes will increase. So the number of cards or number of coins or number of dice can vary, right? But that will vary according to it. So I think it's very clear what is an experiment. So now let us go to the next. Let us go to the definition of, definition, sample space. Now this is a very, very important concept, because whenever we do an experiment, there are some outcomes which are expected out of it. So set of all possible outcomes out of that experiment is called a sample space, right? So sample space S is denoted by a set of all possible outcomes of an experiment. Is called a sample space. Sample space can be visualized by referring to set theory like this. That sample space is like a universal set in the set theory. So universal set of set theory is generally denoted by this rectangle. So this is a diagram for sample space. So all possible outcomes are in this rectangle, right? So that is the visual form of sample space, right? So let us take some examples. Number 1, a coin is tossed. We have already seen this. Coin is tossed. Then what is the sample space? Very simple. Either it will be head or it will be tail. Second, suppose 2 coins are tossed. Then what is the sample space? Sample space is TT, TH, HT or HH. What does that mean? Both are tails, one tail, one head and one tail, and HH, right? So this is the sample space, right? Now instead of 2, now let us take 3 coins are tossed. Now if 3 coins are tossed, what is the sample space? It is, let us start with TTT, then we'll introduce one H in it. So TTH, then we'll remove this H. So that is THT, and lastly HTT. Okay. We started with our triple T. We could have started with triple H also. So H, H, H. Then introduce one tail in it. So and keep wagging the tail. So H, H, T, then H, T, T, H, and then T, H, H. Correct? So this completes our sample space. You will realize that there are exactly 8 possible outcomes. Here, the number of outcomes are 4. Here, the number of outcomes are 2. This is 2 square and here it is 2 cube, which is not a coincidence. So remember one thing, right? So one coin, 2 outcomes. 2 coins, 4 outcomes. So this is 4, means actually it is 2 square. Actually, this is wrong. It should be 2 square and this is 2 cube. Okay, fine. Now let us continue on the next page. Okay. Now, let us take another example of a sample space, right? So, fourth example is, suppose tossing a die. Now the sample space S here is 1, 2, 3, 4, 5, 6. Because the die has got 6 spaces and they are all numbered, and once they are numbered, the all possible outcomes which will come on the outermost face are all actually 1, 2, 3, 4, 5, 6. So the total number of outcomes here are 6 raised to 1, right? Now instead of one die being tossed, 2 dice are tossed, are thrown or tossed, whatever. No? So in that case, the number of outcomes are going to be 6 square. That is what? 36. And it will be like this, So it will be 1, 1, then 1, 2, then 1, 3, 1, 4, 1, 5, and 1, 6. Now we'll start with 2, 1, like that. It will go on till what? 2, 6. Then you start with 3 here, 3, 1. Then it will be 4, 1. Then it will be 5, 1. And then this will be 6, 1. And this will reach 6, 6. You can complete this entire table. Okay. So these are the possible outcomes. So total number of possible outcomes are 6 square, that is 36. And therefore, this is the sample space for throwing 2 dice. Okay. Now, of course, these experiments are very easy, and for you, you can enumerate all the outcomes. Sometimes it is not possible to write down all the outcomes. Okay. So in that case, we will have to go to the next page again. So now let us see. For example, if you take a sample space of such examples like a card, one card is chosen from a pack of 52 cards. Now this requires the concept of combination because it's a selection. So the answer will be what? 52C1. But this is not the entire sample space. If I want to write the entire sample space, I will have to write down all the 52 outcomes, which is not practical. So it could be anything between 1, 2, 3, So 13 spades, then 13 clubs, then 13 diamonds and 13 hearts, like that. So there are 52 outcomes, right? So here only number is important, and number can be calculated by using the combination formulas. If 2 cards are chosen, suppose instead of 50, 2 cards are chosen. 2 cards are chosen, then the outcomes will be 52C2, which is quite huge because it is 52 multiplied by 51 divided by 1 multiplied by 2. You can imagine this number is going to be very, very high, large number. Okay. So like that. So this is how the sample spaces are being created and calculated. Okay. Now let us go to the very important concept in probability, and that is called event. Event. So what is event? Any subset of a sample space is called an event. An event. So this corresponds to the subset concept of in the set theory. So if this square or rectangle, whatever, indicates sample space, then a part of this sample space will be what? A subset. So this is an event, So the points inside this will be remaining an event, okay? Any subset, okay? Now remember any subset. So therefore, immediately we come to know what are the types of events. Types of events. We all know that every universal set is a subset of itself, right? So therefore, that is called sample event. Sample event will correspond to sample space itself, because sample space is an improper subset of sample space, correct? So it contains all possible outcomes. It is called sample event. Exactly opposite of this is the impossible event. Impossible event. Impossible event, or it is called null event. So it corresponds to empty subset. Phi, empty subset. For example, if I toss a die, and if I say that I am interested in the event outcome to be equal to 7. Now that is not possible, because total number of outcomes are only from 1 to 6. There is no 7th outcome. So that is an impossible event. So that is called impossible event. This has no elements at all, and this has all possible elements. So it has all possible elements. And it has no elements at all. Correct? These are exactly opposite of each other, right? So apart from that, let us go to the third type of events. They are called mutually exclusive events. Mutually exclusive events. Now, what do you mean by mutually exclusive events? If two events do not have anything common, right? If two events do not have anything common, then they are mutually exclusive. In set theoretic language, if A is an event and B is another event, then they do not have anything in common. That means A intersection B is what? Empty, right? So these are called the mutually exclusive events, okay? So now, next is, let us say, OR event, or before that, I will say compound events. Here, we are taking two or more than two events and combining them, right? So, combination could be of the two form. One form is called OR, A or B, that is called OR event, or A and B, that is AND event, right? Now set theoretically A or B indicates A union B, and set theoretically A and B indicates A intersection B, correct? So these are very well known and most general operations in set theory we have come across, right? So the corresponding event is referred to as OR event or AND event. So I'll give you an example. Suppose there is a sample space S, right? S contains elements 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10, correct? So this is now let us take an event A, So A is an event which contains 1, 3, 5, then 7, 8, 9 and 10. This is event A. Now this is event B. Event B is 2, 4, 6, 7, and 9, 10. Correct? So these are the events A and B. Now what do you mean by A or B now? A or B means what? That means I will take every element which appears either in A or in B. It may appear in both, but I'll take it only once. So 1 has come here. So 2 also has appeared here. 3 has appeared here. 4 has appeared here. Here is 4. 5 is there. 6 is there. 7 has appeared twice, but I will take it only once. Then 8 has appeared. Then 9 has appeared twice. 10 has appeared twice. This is A or B. Correct? So this is denoted by A union B. A union B. Correct? Now, next is A and B. That means those outcomes which are in both possible sets, right? So 1 is not common, 3 is not common, 5 is not common, 7 is common. You can check that, right? So 7 is in both. Then 8 is not in the both. 9 is there, yes, 9 is in the both. So therefore 9, and 10 is also common. So it will be 10. So this will be A and B, right? So outcomes which are in A as well as B, this will be denoted by A intersection B, correct? So this is A intersection B. Another thing is there is called complementary event. Complementary event. Now suppose this is a sample space. Okay, this is our sample space. Okay, and this is the set A, right? So this set A is dividing this entire sample space into two parts, elements which are in the set and which are outside the set. So elements which are outside the set is called A complement, and that is called complement of a set, right? Or it is denoted, so set of, so if A is an event, if A is an event, then set of all those elements from the sample space which are not in A, right? That is called A complement. It's called A complement. Now A complement is denoted by either A dash or A bar, whichever I like sometimes, right? So A bar is the set of all those elements which are not in A. So this is A bar, correct? So that is A bar, not this one, right? So okay, I'll draw another diagram so that it will be concept is very clear. Okay. So what I wanted to say is this, that if A is this is a sample space, and if this is the set A, the elements of S which are not in A can be shaded like this, So elements which are not in A. So this entire remaining part of this square or rectangle is A complement. So these are the basic examples of sample space. Okay. Now we have seen only one concept needs to be introduced now, and that is exhaustive events. Exhaustive events. So 2 or more events are said to be exhaustive if their union is entire sample space. Correct? For example, suppose sample space consists of all the numbers from 1 to 10. Suppose you have a set A which is consisting of 1 and 2, set B, which consists of 4, 6, 8 and 10, and set C. So this is set B, and there is a set C which consists of what? Set C consists of say 1, 3, 5, 7, 9, right? So these are the elements in this. Now if I take A, union B, union C, then I will have to include 1, 2, then there is 3, then there is 4, then there is 5, then there is 6, 7, 8, 9 and 10, all. So these are examples of what? Exhaustive sets, because they complete, if they combine together, they get the entire sample space.